So far, all the functions that we have considered, we always end up with the value at which the function being considered seem to approach a certain number, and we claim that that number is the limit. But does this value always exist? The answer to this question is no. For a given function and the point, say C, the function may or may not have limit at C. But what does it mean to say that a function has no limit mathematically? What are the conditions or cases for a function to have no limit? To answer this question, we will have to look back at the definition of limit and see how can a function fail to meet its conditions. Let's go. To understand the case of non-existence of limit of a function, it will be helpful to bring back the informal definition of limit. If f of x can be made as close as desired to L by making x close enough to C, we say that the limit of f of x as x approaches C is that number L. In other words, the limit exists and it is equal to L. Hence, to say that the limit does not exist entails showing that f of x cannot be made as close to any number as desired, no matter how close x gets to C. This phenomenon happens in three cases. Case 1 is called the mismatched behavior. This happens when f of x approaches a certain number or a number from the left of C that is different from what it approaches from the right of C. Case 2, the unbounded behavior. It occurs when f of x goes to either positive infinity or negative infinity. Case 3, the oscillating behavior. This happens when the function goes back and forth between two values nonstop. Let us first talk about mismatch behavior. Example, let f of x be defined as the absolute value of x over x. As x approaches 0 from the left, the value of f of x are -1, -1, -1, all -1. Therefore, the function approaches -1. How about from the right of 0? So we assign these values of x, and the computed values f of x is always equal to 1. Therefore, f of x as x approaches 0 equals is approaching 1 from the right. So what can we say? There is a mismatch. When this case occurs, we say that the limit of f of x, or the absolute value of x over x as x approaches 0, does not exist. We can also simply write it this way. DNA does not exist. When the function is viewed through its graph, the absolute value of x over x, we can easily tell that indeed f of x is approaching two different values. So approaching -1 here and approaching +1 here from the right of 0. Let us consider a piecewise function defined by x squared minus 2x plus 1 when x is greater than 1 and equal to 1. Then 2x minus x squared when x is less than 1. We will investigate if the limit of f of x as x approaches 1 exists. As this is a piecewise function, we need to be careful when evaluating the assigned values. Here, pieces of functions takes on different set of subdomains. As usual, we assign values from the left and from the right of C. Then solve for f of x. We evaluate f of x on this function down here. So that's the value that we get. For values of x greater than 1, we use x squared minus 2x plus 1, that one here. And we will get these values. So the result is quite telling. From the left, f of x is approaching 0, right? While from the right, x is approaching 1. So from left, 1 I 0, and from right, approaching 1. So it's a mismatch case. So we say that the limit of f of x as x approaches 1 does not exist, or DNA. Again, this behavior can be easily seen from the graph of the function. All right, so next case is unbounded behavior. When a function exhibits an unbounded behavior, it demonstrates either an unbounded decrease or unbounded increase, or both. In all of these scenarios, the limit of the function fails to exist. In the case of first and second diagram, we can be more specific. Since both from the left and from the right decreases without bound, we can write limit of f of x as x approaches c equals -infinity for this one. Well, for this one, because the graph goes up without bound, we write infinity or positive infinity. Okay. However, it is important to note that the symbol limit of a function equals infinity or negative infinity does not imply that the limit exists and equals to infinity. That's not what we mean or what we want to imply by writing equals infinity. We simply want to say that the limit does not exist because the function increases without bound. Take for example the function f of x equals 1 over 2 minus x squared. This is the graph. As x approaches 2 from either side, notice that the graph of the function keeps going up and up and up. So here f of x tend to positive infinity as x approaches 2 from either sides. So we write the limit of 1 over 2 minus x squared as x approaches 2 equals infinity. If we look at the numerical manifestation of such behavior, it shows that as x approaches 2 from either sides, the value of the function explodes to a larger and larger values. Look at these values. The function shows no sign of converging to a specific value. Instead, it keeps increasing. Therefore, limit of 1 over 2 minus x squared as x approaches 2 equals infinity. Other functions with unbounded behavior are at certain values of x, aside from rational function, are f of x equals secant x. Um, so here there are values of x at which this function does not exist. There are many of them, as well as for a function cotangent x. Finally, the third case for non-existence of limit, it happens when the function oscillates. Oscillating behavior occurs when the function exhibits repetitive and periodic behavior as the input variable approaches a certain value. For example, the function cosine 1 over x, as you can see, the graph gets crowded as x approaches 0. As you can see, the graph keeps on going back and forth. In fact, this behavior will continue indefinitely as x approaches 0. Therefore, we say that the limit of the function does not exist at x equals 0. Imagine that the function seems to go somewhere, but it's not really going anywhere.
How to justify or prove that the limit does not exist based on the definition of limit?
That is a very valid question. And to answer that, we need to go back and summon the formal definition of limit. So we say that a function has a limit L as x approaches c, provided for every epsilon greater than 0, there exists delta greater than 0, such that if the absolute value of x minus c is in between 0 and delta, then the distance of f of x to L is less than epsilon. Because we want to refute the candidate limit is not really the limit, we need to find an epsilon so that for every delta greater than 0, the assumption that the absolute value of x minus c is in between 0 and delta cannot imply that the absolute value of f of x minus L is in turn less than epsilon. To illustrate this, let us use an easier function to handle. The one that we used before, we f of x defined as absolute value of x over x. We saw that it has no limit at c equals 0. That is, the limit of absolute value of f of x over x as x approaches 0 does not exist. Here we will proceed using the proof by contradiction. Suppose, on the contrary, that the limit exists and is equal to L. Therefore, for any epsilon greater than 0, there is delta such that the absolute value of this function minus L is less than epsilon whenever the x minus c is in between 0 and delta. That means, so this is the other way of rewriting this expression. And we also absolute value of x minus 0 is simply absolute value of x, and when you rewrite it, it this the way to rewrite. Okay, now take epsilon equals absolute value of L. We are suggesting an epsilon value which is absolute value of L, and now we will try to find a contradiction. If L is non-negative, now we replace this value of epsilon, the absolute value of L, then we replace it here, and then we transpose the L. That's why we get this expression. Okay, and because L is non-negative, this becomes 0, and this becomes 2L. All right. And can you see a contradiction? Yes, there is a contradiction since within the delta restriction, um, here x is in between negative delta and positive delta, and therefore you can find values of x that are negative. And if x are negative, then this expression here will be negative. And if this is negative, then it is a contradiction because 0 cannot be less than negative. All right. On the other hand, if L is negative, then we get 0 here because this is negative, this is positive, so this is 0. And using the same reasoning, um, we can find x in between negative delta to delta. So there is a positive value in this neighborhood that gives us that makes this a positive, right? If x is positive, then this is positive, and that is a contradiction. This is positive less than 0. That cannot be possible. So we assume the contradiction, and then we assume otherwise, and we arrive with a contradiction, and that is enough to say that the limit really has or the function really has no limit at 0. So we suggest epsilon, and we should find delta to satisfy that requirement, epsilon requirement, but there is no such delta.